The problem should disappear once all of the previous
Yeah.
reminders run out.
Yeah. Because the one that I've been sending them to, I've been sending them reminders for extra 3 months before I start texting them.
Okay.
So, but yeah, sooner with this next wave that I do, which will probably be this coming weekend, that should all be okay. But I'll make an announcement saying that.
I'm seeing new members joining up. Okay.
Yeah, one today. There was one today.
Yeah,
Yep, new guy today joined up. Yep.
I just overheard the conversation. I'm having that issue. Renewal. It's not
A renewal, you're having trouble with it. Email me and I'll send you a proper link.
I have a membership, right?
Yeah,
I've done that.
When did you do that?
Just now.
Oh, good. I'll pick that up tomorrow morning. And I'll deal with that tomorrow morning. Yeah, we've had a change of platforms and I'll just do an announcement about it. Yeah, but you've done the right thing. Yeah, cheers. Oh, hey, John. Nice to see you. Oh. I'll wait till 8 o'clock because people still arrive, and I'll do the handouts. Yeah. Rather than, so as people arrive, because we always have chocolates in our quiz night, and rather than break up all the throw
Pretty good.
Shall I turn the lights down one more step, just down to low? I think we put them down to about there, don't we? That works out well. Oh, good. Okay. Well, welcome. I think this is the last introduction to astronomy for the year. So welcome. Thanks for coming along. And it's our annual quiz time, whereby these are some of the topics we're covering. And we're going to review, just some brief review. It's just all multi-choice. It's all fun. It's non-threatening. There'll be some reviewing some topics we've talked about, and I've taken the opportunity to introduce some new topics, topics that you want to chat. I wouldn't mind 15, 20 minutes of your time just to chat about, but not long enough to put a full 1 hour talk. So I've just slipped them in here. So anyway, so it's all good fun. So these are the topics we're going to cover today. So first of all, we're going to talk about the sun. In May this year, we had some fantastic aurora, beautiful. And so I did a talk in June. I thought, well, that's a no-brainer what I talk about in June. We talked about the sun and the southern lights, what's going on. So we talked about some of the structure and functions of the sun, what was going on. So I thought that would be a good one to start off with. And just online, I saw some great pictures here. This astrophotographer, Mark Johnson from Arizona, USA, it was space.com. They had some of those great images. So I've just stolen a few of those tonight, giving them credit, of course. So the first question up, what surface features of the sun give it this fuzzy appearance here? I'll go through them, then I'll blow that picture up for you a minute to have a better look at it. See that A, spicules, B, solar prominences, solar flares or sunspots. So let's just bring this picture up. So what I'm referring to is not these areas over here of these solar prominences, but all this, it looks all fuzzy, doesn't it? It looks like a shag pile carpet. Yeah, so out of what gives it that fuzzy? Any takers for A? Yep. Any takers for B, C, or D? Sunspots. Yeah. Okay. The solar. The answer is A, spicules. And let's just have a chat about, and that's what today's all about, is to actually have a chat about what the subjects are. So this is the surface of the sun, what it looks like, just a diagram. This piece here is called the photosphere. That's essentially the surface of the sun, the visible surface, what we see as the surface. It's got a depth of about 400 kilometres. Surface temperature is about 5,800 degrees. Then above it, here's this sort of irregular fuzzy layer known as the chromosphere. And that varies in height anywhere usually between about 3,000 to 5,000 kilometres high. But these are these spicules shooting up here. So let's have a closer look at them. And that's a nice close-up. Look at these, all big furry stuff. But it's so misleading. It looks like a shag pile carpet or some fuzzy little things flapping around in the breeze. But what you're looking at is millions of jets of plasma that are just propelled, shooting upwards. The average spicule that you're looking at, diameter, 300 kilometres diameter. Yeah, that's the distance, because I mapped it out on maps. That's the distance from Orio, just north of here, to Taupo. That's 300 kilometres. So that's just the diameter of these millions of spicules shooting upwards. Yeah, 100 kilometres per second. We'd be driving down to Taupo at 100 kilometres per hour, but 100 per second. They last for about 15 minutes before they collapse. Yeah, and they get to altitudes of 10,000 kilometres. That's the distance from Auckland to Los Angeles. So you imagine that going straight up in the air, and that's these spicules just every 15 minutes are just rocketing upwards at 100 kilometres per second with a diameter of 300 kilometres. So it's very, very deceiving. So that's what gives the sun that fuzzy appearance. So what drives them? And they don't know for sure, but they speculate and have a good educated guess. They're most likely just knots of magnetic energy that snap open at the surface and just release, the magnetic activity tries to keep the surface down and the magnetic loops just snap and release plasma energy up as these sort of spikes, if you will, or spicules. And that's what's going on. But look, here's a beautiful side-on side-on picture of it here, these spicules. Here it is, nice little movie clip. Look at that.
So it's an animation or?
It's a little GIF file, a little animation, a little GIF file. A lot of these actually images are from the Solar Dynamic Observatory from NASA. And I'm unsure if that is or not. Okay, so what are the dark features? And there's one right here. This, once again, is from this astrophotographer. Look at the resolution of that for an amateur astrophotographer. Just brilliant. So these dark spots here, are they A, spicules, solar prominences, solar flares, or sunspots? Let's have a closer look at them there. Once again, you can see all these sort of, the swirling here of spicules, but there's a nice big dark area there. So, yeah, who put D, sunspots? Yeah, they are sunspots. And they're indicative of how active the sun is. Just having a closer look there. So what you're looking at is, that's still a hot area. You're looking at regions of the sun where there's intense overlying magnetic field lines that are suppressing the hot plasma trying to come up. So elsewhere, look around here, you've got hot plasma, these little cells, like convection cells, rising here, and the dark little strips is where it's falling down to one side of this, down each side of the cell. So the surface temperature of the sun is about 5,800 degrees. You're looking here, it's still damn hot, about 3,500 degrees, but it's just cooler, so it looks darker. So that's what's happening. It's the intense magnetic fields are suppressing the rising hot plasma coming up in convection cells. Essentially what you're looking at, the convection cells is like boiling water. You know, your bubbles of water, cells of water come up in your hot electric jug in the morning. And just looking through the cross-section of the sun, that's what you're looking at here. You're getting intense magnetic fields, and often what does happen is then they loop up and they go back down through another area. And where these two areas where they enter and leave the surface of the sun, this photosphere, they're intense magnetic regions. And of course, so they're slightly cooler. So you'll often get them in pairs. And here's some little groups and pairs. Sunspots are big, like here's a comparison against the size of the sun, against the size of the Earth. And the Earth is roughly about 13,000 kilometres across. So that gives you an idea there. So yeah, the typical diameter range, yeah, anything up to 50,000 kilometres across these sunspots. And they can be, so that's your typical, when they can get up to about 80,000 kilometres across. Amazing. They can last anywhere between 1 and 100 days, and where you get groups of them, like here, little crops of them, they can appear for up to about 50 days, and often then they disperse or settle down again. So that's sunspots. So, once again, look at the resolution from this guy, Mark Johnson in Arizona. So what are those explosive eruptions? So what you've got here is looking at big explosive eruptions. Now the key to this here is that this is, and because you could get this wrong, this here, notice it's still anchored down to the photosphere. It's not shooting off. So what are these? Spicules, solar prominences, solar flares, or sunspots? Who got B? Yeah, they are, and that was the first slide too. They are. So what you're looking at here, this solar prominence, is 160,000 kilometres high. That is reaching out, huge. And the key to it, you might think is, gosh, I didn't put in there to confuse them. You might have thought that was a coronal mass ejection. A coronal mass ejection is like a more aggressive form of that, and then the magnetic fields that are holding them down snaps, and it just throws out a huge, big chunk of the plasma. Actually, gets thrown out, but it's still anchored down here. And it was only this afternoon I found a lovely little picture. This shows it nicely. You can see it, but would be a big magnetic loop here, and it's coming back down again. And this more clearly shows it's being anchored down. And there's the size of the Earth. So the prominences, they're anchored down to the photosphere, but they can last for days or months. And if you see photographs of a total solar eclipse, or you're lucky enough to see one, you see these big crimson-coloured solar prominences that you see. And they're just hanging around. You don't see them rise up like that and fall down. They just sit there, and they can sit like that for months, just sort of poised. Okay, so that's the first question. That was just about some of the solar activity. And of course, the sun goes in 11-year cycles, and we're heading right now into 2025 with solar maximum, a lot of activity. So you'll probably see a lot of this sort of stuff going on. We'll get more aurora, hopefully. Now, we're going to talk about brown dwarfs. Who is familiar with brown dwarfs? Yeah, because we don't talk a lot about them. I'm guilty of the same. We tend to skip over them. So brown dwarfs are either A, spectral class K and M, F and G, often have lithium in their spectral lines, or none of these. I don't expect you to say that. The answer actually is C, and I'm going to show you why. And I'm going to show you what those spectral classes K and M and F and G are all about, and I'll show you why you get lithium in the spectral lines of brown dwarfs. And that's one of the ways they call it the lithium test, how you identify them. So let's talk about brown dwarfs. First of all, let's take a step back and let's talk a little bit about stars. By definition, what a star is, it's a big spherical ball of hot plasma that's held in place by the force of gravity, and the key to it, it's self-luminous. And that's important, because why is this huge big ball of hot plasma self-luminous? It's self-luminous because at its core it is fueled by, here's the word too, sustainable nuclear fusion. So a star to achieve that must be a certain size, a critical size, sufficient to have enough mass to generate enough gravity, inward force of gravity, to create sufficient temperatures and pressures at its core to fuse nuclear fusion, sustainable nuclear fusion. And all stars in the first 90% of their lives are what we call on the main sequence, just a term, whereby by definition they're fusing hydrogen into helium-4. So that's by definition, that's sort of how they attain it, by being up to a critical mass. And there's a reason I went over that really simple explanation of what a star is. It's a spherical ball of hot plasma, self-luminous, because it's got enough mass to generate enough force to create sustainable nuclear fusion. So that's an important little definition there, because it's very relevant to how you define a star. So the next stage from there, how are stars classified? And they're classified essentially by the temperature and what these astronomers see in the spectroscopy. Spectroscopy is when they put a spectroscope on their telescope and it's able to split the visible light into all its different wavelengths, or colours of the rainbow, if you will. And they then plot here the intensity of light on the y-axis, the nice little graph, versus the wavelength. And they measure the wavelength each time and measure the intensity. And they get various graphs with these sort of shape. And where it peaks with the particular wavelength is a very, very simple formula. They can tell the temperature of the star. So that's how they tell the temperature. And it's then confirmed, and they get more an idea of the star's spectra by having a look at the light and analysing the atmosphere of the star. In particular, they're interested in what elements are present, but importantly, what energy states, how excited are they? Is that a particular element just as it is, with all its electrons intact, or is 1 or 2 or 3 or 4 electrons being booted off that element that's excited, what they call ionised? So it's the different wavelengths where it peaks for the temperature, and they're interested in what elements and what energy states in their atmosphere. And from that, they're able to infer not only their surface temperature, but what we call their spectral classes. And they start off hot here, about surface temperature of about 25,000 degrees, and go down to about 2,500 degrees. And they're numbered here from the most hottest one. Of course, this is not to size, because down at this end, they're a heck of a lot smaller and a lot bigger here. But just for simplicity purposes here, they've put the colours in for us. They go from a bluish white, they go right down to red. And they're labelled O, B, A, F, G, K, M. And I know what you're thinking. You thought, gosh, when I went to school last, the alphabet went something like A, B, C, D, E, and so on. Well, that's historical reasons. And stars were classified by A, B, C, D, E once upon a time based on how much hydrogen they could see in their atmosphere. But then as they learnt more about stars, they realised that's not a smart way to classify stars. It's best to go from hottest to coolest. But they kept the numbers or the letters that are being allocated to each type of star, they kept that in place. And if you want there's a very common mnemonic to remember that, is O, B, a fine guy or girl, kiss me. And that's the general sort of mnemonic for remembering those. So that's the general spectral classification of stars. all those, by definition, are going to be big enough where they've got enough gravity to create enough inward force, to create enough hot temperature and pressures at their core for sustainable nuclear fusion of hydrogen into helium-4. Now, that's where our sun sits. Our sun is a G2 class, so our sun sits right there. It's a yellowish green star known as a G. It's an average sort of star. Okay, then there's been a few more additions. Wolf-Rayet stars are sort of very massive, unstable stars. They're labelled as W. And then there's some red giants which have acquired, some of them are very rich in carbon in their atmosphere, more so than their oxygen. So they're called C-class for carbon stars. Then you get some red giants on a certain part of the evolution stage called the asymptotic giant branch. They have an equal mix of carbon and oxygen. They're called S stars. Then D for white dwarfs. But that's by and side. What we're interested in today is this little class here, L, T, and Ys, brown dwarfs. And they've just tacked those on, and as you'll find out, brown dwarfs are not considered proper stars, which we'll explore why. But they've put that LTY. And the mnemonic for that is, oh be a fine guy or girl, kiss me, like this, yo! So that's, so that's a little tack on mnemonic. They get down, their temperature range, what we're going to be talking about brown dwarfs, anywhere from about 2,500 down to about 200 degrees. So they get very, very cool. So let's talk more about them. And here they are, the classes L, T, and Y, and what they call late M. That just means the cooler end of the M scale. Like all of those letters there have got scales between 1 to 10 themselves. So the cooler end of the M classification are also, a lot of them are brown dwarfs as well. So there's no fine cut-off point necessarily with the spectral classes. So brown dwarfs are often considered the missing link between stars and exoplanets. You might think, why is that so? Let me explain. The bottom line is they form like stars. So stars form from big, massive clouds, big spherical cloud of gas and dust that under self-gravity, they start collapsing and start spinning faster and faster, and they collapse in on themselves, and then you just get a hot spinning star at its center. And that, by definition, is a star in terms of that's how stars form. Planets form by a different method. That new star that's formed, a lot of it, then a disk forms around that, a protoplanetary disk, and the planets form through various mechanisms, including gravitational collapse and accretion, in the disk that goes around that star. So there's a difference between how stars form and how planets form. But so brown dwarfs are the missing link. They form exactly like stars from a big spherical cloud of gas and dust through self-gravity that collapses in on itself, but it does not have enough mass to have enough inward force of gravity to create the conditions of temperature and pressure at its core for sustainable nuclear fusion. So it's just that nice missing link. It's not a planet and it's not a star. It's formed like a star, but it's not a star by definition. So this is where they all fit in here. And let's start on this side here. It's on the right-hand side. Here's your stars, and they're called red dwarfs. Now, I'm just going to introduce a little idea here, is that how do you measure and talk about the mass of a star or a planet and so on. And red dwarfs, for stars, you tend to use solar masses, the mass of our sun. That's one solar mass, it's one unit. So red dwarfs, these are those with the K and M classes down the cool end. They're known as red dwarfs, and they anywhere between 8% and 80% of the mass of our sun. So 0.08 to 0.8 solar masses. And they sit over here. They've got enough gravity, enough mass to create enough gravity to create the temperature and pressures to fuse hydrogen into helium-4 at their cores, and that's sustainable nuclear fusion. So by definition, you've got a star. On this side over here on the left, you've got your planets and exoplanets. And when you start dealing anything under the size of a star, you start using Jupiter masses. So one mass of Jupiter is one unit. And anything up to about 13 Jupiter masses, as a rule of thumb, is an exoplanet usually. Because sometimes you might think, well, what's the point? We know about if you see them in a solar system, you're not always going to see them in a solar system. Remember the talk on the James Webb Telescope, they're picking up more and more rogue exoplanets where a planet has formed in a planetary system through dynamics, orbital dynamics and so on. It's got expelled from its solar system and it's wandering aimlessly, called a rogue planet, just wandering through the galaxy on its own. When you see something like that, you've got to decide, am I dealing with something like a rogue planet, or am I dealing with a brown dwarf? Because you think, well, it's not quite a star. Or am I dealing with a low red dwarf, a really low dim red dwarf, which we'll talk about. So as a rule of thumb, this is where the brown dwarfs sit in. They're usually between 13 and 80 Jupiter masses. So it just gives you a bit of a guideline. And their spectral classes, the cool end of the M's and the LT's and Y's. So those are your brown dwarfs, and that's where they fit in. So you can see why they're called the missing link between here. So they look like exoplanets in a way, and they don't have nuclear fusion, so they're not a star, but they formed through the same process that a star would have formed. Let's just look at their size in perspective, because you'd think they'd be a lot bigger than they actually are. And here's a nice little diagram here, an artist's impression. Here's our sun sitting here. Here's a low mass star, in other words, a red dwarf, which is a certain size. Look at the sunspots, which we've talked about here, all over them. And you can see here that these are glowing quite a bit more. These have enough mass to have the right conditions for sustainable nuclear fusion. So here's your Jupiter here, Jupiter mass, and that's one Jupiter mass. And here's a brown dwarf. That's somewhere between 13 and 80 Jupiter masses. But you think it should be a lot bigger than that proportionally. They are not. They're only about 15 to 20% bigger than most of the large exoplanets. Why? Is because they don't have nuclear fusion going on in their centres. So they haven't got this huge, strong outward force pushing against gravity, that's trying to bring them in and pushing them out again. So they're not puffed up as such. It's just pure gravitational contraction that's just squeezing them down. So they're just really, really dense. So it gives them, so they're not necessarily a big volume. They're just very, very dense. And that's the principal cause of their glowing faintly at infrared wavelengths. It's just the gravitational collapse because there's no nuclear fusion pushing them out. So they just quietly grow in the infrared through that whole issue of gravitational collapse just coming in on them. So you can see there, so they're dim, they're in infrared wavelengths, and they are relatively small. They're not big, so they're not easy to detect. So when you do see one of these objects going through the galaxy, and you say, oh, there's something glowing in the infrared, is it a brown dwarf or is it a low mass red dwarf? Which is it? How to know? And so to answer that question, let's have a look, let's lift the hood and have a look and see what's going on inside them. To your left here, you've got a red dwarf, and it's got enough mass to generate sustainable nuclear fusion. So that's got what we call fully convective sort of layers going on here. So that's what's going on inside a red dwarf. Over here, you've got your Jupiter, your planet, and there's just nothing going on in here. It's not enough mass to have enough gravity, not only to not have nuclear fusion, but also not enough to really cause a great big glow in infrared through gravitational collapse, or gravitational contraction, I should say. Your brown dwarf is in between. It's got that gravitational compression going on that's high enough to create a dense enough object where it starts glowing in infrared wavelengths. But there's also another reason why that adds to the glow, but it is the gravitational contraction is the main reason they glow, not the nuclear fusion. When that initial cloud of gas and dust started collapsing into itself, that interstellar gas and dust in that cloud had a little bit of deuterium. That's an isotope of hydrogen. So it's one proton and one neutron, bit of deuterium. And there was a little bit of that in the mix anyway. And brown dwarfs, a lot of them have got the ability, some of the higher ones in particular, they actually do have enough pressure to burn through that little bit of deuterium that's in there. And when they're very young, they're often at their brightest because of that. It's got a little bit of low-grade deuterium, but it chews through and depletes that deuterium fairly quickly. So a brown dwarf will have a slightly higher glow when it's young because it's burning a little bit of deuterium. And that doesn't take too much energy for it to do, and that puts it into helium-3, but eventually the deuterium runs out. So, yes, for a small amount of energy for a very short time, but gravitational attraction is the reason it glows in that faint infrared. And there's another thing called the lithium test. And that brown dwarfs, less than 65 Jupiter masses, they cannot burn lithium at all. Where did the lithium come from? That would have come from, once again, just the interstellar or the large molecular gas and cloud that it originated from. There would have been some lithium in there as well. And if you see lithium in their atmosphere, you know you're dealing with a brown dwarf that's less than 65 Jupiter masses. Anything greater than that, it's got enough energy, enough mass rather, to generate enough forces to chew through its lithium. So brown dwarfs greater than 65 Jupiter masses and red dwarfs rapidly deplete their lithium. They've got enough to burn through their lithium, but they deplete their lithium very, very quickly. So if lithium is present, they call it the lithium test, it means you're dealing automatically with a brown dwarf less than 65 Jupiter masses. So that's one test you can do. Or if there is no lithium there, it means you're dealing with a massive brown dwarf or a red dwarf, but very, very young. So you distinguish them further. You look at other things like their luminosity, their size, and so on. So there's another one. Brown dwarfs have methane in them. So if you see methane in it, you know you're dealing with a brown dwarf as well. Because methane, CH4, it's a molecule. So red dwarfs are just too hot. Their surfaces are too hot. It will just pull the carbon and the hydrogen apart. You need to have something cool enough for that. So you'll see methane in the atmospheres of brown dwarfs. So that helps you further. So there's all these little tests you can do, because at first glance, you don't know necessarily whether you're dealing with a brown dwarf or a very or a lower, one of the cooler red dwarfs. So those are some of the tests that astronomers use. And then there's the whole object of, are you dealing with a very cool brown dwarf or a large exoplanet, a rogue exoplanet that's just roaming the galaxy? That can be very hard to differentiate between the two. And for that reason, a lot of astronomers just call them substellar objects, too, because it cannot be easy. So you can see why everyone avoids the topic of brown dwarfs. But I thought I'd step out and bring them out. So most brown dwarfs will go through these 4 stages. So they'll start off at a late M dwarf, in other words, the cooler end of the M spectral class. And that's when they've got a little bit of, they're burning that little bit of deuterium, so they've got a bit more of a glow to them. So they're sort of the cooler end of the M, and they're identified by having in their atmosphere titanium oxide. Once again, anything too hot, and you wouldn't get the titanium oxide, it's just too hot for them to join up. Then they start, naturally, they're going to run out of deuterium, and they go through a natural cool down process to become what they call an L dwarf, a T dwarf, and a Y dwarf. And in each stage, you start seeing different things in the atmosphere of these brown dwarfs. So you're going to be looking at their temperature. You're going to have a look what atoms, and then can you see molecules and compounds in their atmosphere, and you get a profile, and from there you're able to build up an idea of whether you're looking at a brown dwarf or a cool red dwarf, and then what sort of brown dwarf you're looking at. So that's brown dwarfs. So yeah, just in summary, so they are small, so they're not really big because they're small, because they're just very dense and compact down. They're very cool because they've really no sustainable nuclear fusion going on. It's just really gravitational contraction that you've got going on that's causing the infrared glow. They're very dim, and you're starting to see atmospheric molecules and compounds. Any questions around brown dwarfs? Yeah, Rob.
The life expectancy going from where they start to where they end up very dim.
Long time, yeah. I don't know the exact numbers for the life expectancy, but they take a long time. I think they just cool down to a certain point and they just sit there, yeah. Yeah, now, what telescope then would be ideal for discovering and observing brown dwarfs? Yeah, and what one did we talk about during the year? James Webb, yeah, we talked about the James Webb. So, got a question for you. So the James Webb telescope is located in space where a geostationary orbit around Earth, in lunar orbit near the Sun-Earth Lagrange point L2, or none of these. So have a think about that. And Who thought C? Yeah, C, absolutely. So we had a good old talk about that when we talked about the telescope. And here it is here, these Lagrange points are gravitationally stable areas where you get a smaller mass object going around a larger mass object. You get these gravitationally stable points that they're labelled. And one of them is called L2. And it's, for the Earth-Sun system, it's 1.5 million kilometres out in this direction, directly in a line from the Sun, Earth, straight outwards. And that's a gravitationally stable site. You've got, if you're wanting to look out the rest of the galaxy, rather, the rest of the universe, you can quite happily point that way, and you're not, and you can block out with a sunshade, which the James Webb does. You can block out the light from the Sun and the Earth. So it's a bit of prime real estate. You've got telescopes there, you've got the James Webb, you've got the Gaia there, and you've got Euclid there at the moment. So when a telescope's done its dash, they quietly save a little bit of fuel to the end, nudge it out of the way, and often another one will take its place. It's prime real estate to sit there. So they don't just sit there like this, they actually do a bit of an orbit in the general region. You can see it's a highly elliptical orbit there, every 168 days, which I think is about every 5 months or so. And you can see at its close, it's about 250,000 kilometres and about 830 there. So it's quite a long elliptical sort of orbit it does. And as the Earth goes around the Sun, of course, L2 moves with it, and that just keeps orbiting around it like this. So the advantage why use it, you're out from the shadow of the Earth, so you've got constant exposure to sun for your solar panels to power it. So of course you have your big shield to keep the heat and the light away from the sun, but you have your solar panels on the sunward side of that. So you're away from the shadow of the Earth, so you always got exposure to the sun. It is gravitationally stable, so you need minimum propellant, that's good. And you're in a direct line between the Earth and the moon. And I think it was the lady in the back, you said, how long does it take the data to get from there? And I think we just worked out, I think it was Niven at the quick as anything, said, well, it's 1.5 million kilometres, light travels at 300,000 kilometres per second, 5 seconds, that's all it takes from the data to get to here. And you're always in line with the Earth. You're never floating over here with Earth over here. You're always in line with the Earth, so you get data directly, only takes 5 seconds, data from here to here. Gravitationally stable, you always got solar power, and you need minimal propellant because it's just an ideal site, particularly for infrared telescopes. It's just a very good site for doing astronomy. So that was L2. Now, an intermediate black hole, this was in July, and was recently discovered where? A, at the centre of the Milky Way, B, in the Orion Nebula, C, in the Pleiades Open Cluster, D, in the Omega Centauri, in Omega Centauri Globular Cluster, or E, Queenstown. Think about that for a minute. And who got D? Yeah, most people got D. So this was an intermediate black hole discovered in July in Omega Centauri. And that, to me, that got my interest. It raised a few little interesting points and implications. So there's two important implications to that, for starters. One is the whole thing surrounding black holes. And the other thing is the talking about Omega Centauri itself. It sort of raised another question. Yeah, what are you about, Omega Centauri? So let's have a look at that. So talking about black holes, traditionally there's been 3 types of black holes that have been sort of thought about. The first is the stellar black holes, and they're anything usually between 5 and 100 solar masses. And that's where you've had a star greater than 20 solar masses, and at the end of its life, nuclear fusion has come to a grinding halt, so the whole star, its core collapses in onto itself, and then the star collapses in on the collapsing core, and it rebounds, all the outer envelopes rebound off the core and scatter, and you get this huge big supernova explosion, but the core continues on collapsing down to become a black hole. So they're called stellar black holes, and there's been plenty of those have been discovered and pointed out and observed quite happily through various ways. The other one is supermassive black holes are being well established, whereby they are masses of millions up to billions of solar masses. And it's now known that at the centre of most decent-sized galaxies, they harbour a supermassive black hole. And that can be an active one if it's still chewing up material it's going past, it spits it out, and so they're called an active galaxy. Or like in the case in our Milky Way, we have one sitting there called Sagittarius A star, and that is just relatively dormant. There's not every now and then a little bit of material goes past, but for all intensive purposes, it's sitting there. There's no large chunks of material. It's just sitting there dormant, nice and quiet. So, but yeah, supermassive black holes. And that's Sagittarius A star, a picture taken from the Event Horizon telescope. And what you're looking at here is this is light. So this is radio telescopes that have done this. So this is radio wavelengths of light being emitted through a process called synchrotron radiation, through high-speed particles racing around, being accelerated and racing around the outskirts of the black hole event horizon, emitting radiation and radio wavelengths, and that's what you're looking at there. But you see in the middle this sort of dark spot here, and that's the shadow of the event horizon of the supermassive black hole in the middle of our Milky Way. Its mass is thought to be estimated to be 4.3 million solar masses, 4.3 million times the mass of our sun. But it's, of course, an infinitely small size, the actual blob itself, looking for a better word, in what we call a state of singularity, which we just don't understand and maths just breaks down. So we don't know much more. But its event horizon, that's the point of no return, where if you go beyond that, you can't go beyond, you can't come back out again, and the gravitational field is so strong that the escape velocity is faster than the speed of light. So not even light, which is meant to be the fastest thing in the universe, not even light can escape beyond a certain point. And that's called the event horizon, or the Schwarzschild radius. And the radius for us, for Sagittarius A star, is about 12 million kilometres. That's not too bad. You might have, that's quite a size, but that's well inside. That's only about a quarter of the size of the orbit of Mercury. So the whole thing is pretty condensed down, but it's 4.3 million masses of the sun. And even the event horizon is inside the orbit of Mercury at only with a radius of 12 million kilometres. Mercury is what, about 56 or 55, 56 or something million kilometres? So that's supermassive black holes. So the ones too. But there's always been this big gap, intermediate black holes, where, and they just haven't been discovered. They obviously fit in there between 100 and 100,000. These ones here, these stellar black holes, you don't get them much more than that, because you start getting stars become unstable, anywhere between about 120 to 150. Those sort of bigger figures of a star of a size solar masses, they're just unstable. So they just don't really hang around for very long. So most stars are sort of top out at maybe 120 or so. So the black hole in the middle, they said 5 to 100, sort of roughly for your stellar black holes. Then the supermassive ones, but they couldn't identify these. So it was just a hypothetical called intermediate black holes that just were a missing link. And it's just only of recent times they're actually finding to discover some of them. And they possibly could be the seeds, because one of the big questions is, these supermassive black holes, how did they get so big so quickly? They're starting to see them now. The telescopes are looking back into the early universe. They're seeing them in the early universe. How did they get there? And they think that possibly these intermediate black holes could be the missing links, the seeds of these supermassive black holes. But suddenly they're starting to discover some, to do some research on and learn more about them. So that's the first implication. As soon as I heard that, we've found an intermediate black hole, I thought, right, that's one implication. Let's talk about that. But the other one thing, it starts raising questions. So first of all, you might think, how did they discover that? Because they can't see these black holes. You look at the orbits of stars around it. They noticed that there was about 7 stars close to the centre of Omega Centauri that were just going a lot faster than they should be. They were obviously going around some huge, dense mass near the centre of the Omega cluster, and they thought, okay, that you can work out from there the mass, and they found an area that fitted the bill, and it was just over 8,200 solar masses. So it fitted beautifully, the intermediate black hole. But so the other implication though is about Omega Centauri itself. Omega Centauri is a globular cluster. What is a globular cluster? There's 2 types of star clusters, the main types. One is you've got your open star clusters, where a massive, big, giant molecular cloud of gas and dust has all started collapsing in onto its self-gravity. But within that, you get these little knots of higher density ones, and they all form individual stars. And you end up with a family of 100 or so stars that have all formed from the same massive big giant cloud, and they all are loosely gravitationally bound, and they just hang out together as a sort of a family for a while, for a few million years, and eventually with gravitational perturbations and so on, they all wander off on their way. And our sun would have formed in an open star cluster. But there's also these globular clusters out there. Usually out in the outer skirts and the halo around the Milky Way. There's about 158 or so that have been discovered around the Milky Way. And instead of just a few hundred young stars, all loosely gravitationally bound together, suddenly you've got thousands of these stars tightly gravitationally bound together, much, much, much more, tightly gravitation to real dense balls of stars. And they're all old stars. You know, you're talking 12, 13 billion years old. Obviously some of the first 1 or 2 generations of stars in the universe. So they're all old stars, all of a similar age. This is your typical globular cluster, and all of the same metallicity. Astronomers call any element heavier or bigger than hydrogen helium, like carbon and oxygen and so on, all the rest of them, they call them metals. It's just a term. And the first generation of stars after the Big Bangs would have just been hydrogen helium, but they would have then forged those heavy elements, or metals, and of course they would have then gone supernova and seeded and dispersed all those metals out. The next generation would have had a few metals in them. So with each passing generation, you're getting a higher percentage of metals, heavy elements. So in a typical globular cluster, they all have very similar metallicity. In other words, the same generation, the same age. So you're getting dense, compact collections of thousands and thousands, sometimes up to millions of stars, tightly gravitationally bound, all the same generation. How did they form? And the general idea is maybe in the early universe, like we see open clusters and galaxies now, the early universe that was a lot more smaller and denser, and maybe these big super open clusters formed, what they call superclusters, with a lot more stars in them, and just with merging galaxies and stuff, they got all flung out to the outer skirts, and they just formed into these dense globular clusters. So that's how they think they probably formed. So yeah, in the outer parts of the galaxies, most galaxies, you see these globular clusters. So that's typical globular cluster. But Omega Centauri is we've known it, it's no ordinary globular clusters. There's been a few interesting features about it. One is it's 10 times more massive than most globular clusters. It's the largest globular cluster in the Milky Way that we can see. It's in the southern sky, it's in Centauri, so you can quite happily see it. Presents even with the unaided eye. You can see it, but it's great through a telescope. But it's massive. It's head and shoulders above the size of all the other globular clusters. So you think, really, what's that about? It's just something special about it. The other thing they've known is the stars in it are not of all the same age and generation. They're all of varying ages and metallicity, or generations in there. So really something is really going on with it. So, and now they've found an intermediate black hole right in the middle of it. And what's in the centre of most decent-sized galaxies? A supermassive black hole. So their suspicions for a long time has been that Omega Centauri has probably not been a true globular cluster. It's probably been the remnant of the central aspects of some previous galaxy that's merged and been canalized by the Milky Way, but that's been its central core. And to us, it just looks like a globular cluster we've just fitted in with all the rest of them. So the fact that they've found now at the centre of an intermediate black hole really adds a lot of strength to the whole concept that Omega Centauri may well be not your standard globular cluster, but in actual fact, the core, the remnants of the core of some galaxy that's come too close to the Milky Way, has been swallowed up and incorporated with us. So that's that came out in July, that little news clip, and I thought that's interesting, that's worth putting in tonight. Whenever you see little news clips like that, immediately you should be thinking to yourself, what are the implications? Not, oh, isn't that nice? Oh, they found an intermediate black hole. I just go, where did they find it? What are the implications of that? It's sort of the things that you sort of start to think about when you start to see astronomy news. Now, who's familiar? This is another one of these topics, like brown dwarfs, I wanted to include. Milankovitch cycles. Who's familiar with Milankovitch cycles? Yes, a few of you and stuff, but it's not widely talked about or known about, so I thought I'd just introduce these. And so Milankovitch cycles involve Earth's eccentricity of orbit around the Sun, which we will talk about. That means how elliptical the orbit is, its axial tilt, or its obliquity, how it tips it over is, or its precession, which we'll talk about all these. And the answer is all of the above. And let's talk about, so I didn't get you to guess that one because it's, I thought I'd just talk about it. So it's named after this guy here, Milutin Milinkovic, and he was a Serbian mathematician and astronomer. And he did a lot of this groundwork actually in the trenches in the First World War. And then he was in house arrest for a lot of the First World War in Budapest. And he did a lot of his calculations. He did pretty much like Galileo. They put him in house arrest for doing something wrong. And he takes advantage of it all and does all these amazing calculations. I think Isaac Newton did the same, didn't they, when they had to shut Cambridge down, or he sat at home on the farm and did calculations. So this guy, he did it in the 1920s, and there was no calculators in those days. It would have been pen and paper. And he realised that there were certainly some features of the way the Earth orbits the sun and the way it's orientated towards the sun that over long timescales would affect the amount of solar radiation the sun is exposed to. And that would have some sort of cyclical effect on the Earth and our climate. And what really inspired him, there's been a lot of evidence over time, they've known it for some time, that Earth's gone through at least a couple of sort of snowball Earths, of glaciation periods. There's widespread glaciation across us, then we have periods of interglacial periods, of warmer periods between those. And he was aware of that, and it just inspired him. He said, I wonder if there's some sort of connection going on there. I'm going to look further into this. And he sat down and did all this sort of stuff, and they're now known as Milinkovic cycles. So let's talk about them. So yeah, long-term variation. So we're dealing in thousands of years here that just alter the amount and distribution of solar energy we get from the sun that influences the climate's patterns over thousands of years. And these are the three things which we're going to look at. So eccentricity, that refers to how elongated, or the opposite to how oval an orbit is. And you can see here, it's labelled from 0 to 1, and 0 being a perfect circle. And you can see the red one here, these little orbits going on here. You can see the red one, that's a perfect circle, so that's called eccentricity of 0. 0.2 is the, sort of the lime green. You go a little bit further out, you can see it's a little bit more elliptical, and you keep going out, and the magenta, the one here is 0.8, but you can see that's quite elongated. You can see this little dot moving along here. So that's how they're rated, between 0 being a perfect circle and 0.8. So all orbits aren't of the same. There's a thing called eccentricity, how elliptical orbits are. Earth's current orbit, this is not to scale. I've just done this, I've exaggerated it just to make a point that we aren't a perfect circle. We're pretty close to one though, but we're not a perfect circle. And the distance between the average distance from the sun to the Earth is known as 1 astronomical unit, which is about 150 million kilometres. So, but you can see here, the months of during the month of early January, the Earth's at its closest, and that's known as perihelion, and it's just under 1 astronomical unit. In the middle of the year, it's called aphelion. I always remember that when you're trying to think of it, A for away, for its furthest point, a little mnemonic way of remembering it, and you can see it's a little bit over 1 astronomical unit. So in the middle of the year, we are a little bit further out from the sun than we are Christmas and New Year time. And this, of course, this is when we have our southern winter solstice, and we have summertime over here. So this is exaggerated a little bit, but it's just showing the point of how we do have an eclipse. We're not a perfect circle.
Chris?
Yeah?
I understood those to be perigee and apogee.
No, perigee is going around the Earth like the moon is labelled apogee and perigee. And then it's perihelion and aphelion for the sun. Going around Jupiter, the moons of Jupiter, they're called apojovian, I think it is, and perijovian. So yeah, they've all got their little things. So perihelion is going around the sun. But yeah, that's raised an interesting point, Keith. Yeah, good. So this is us here. Let's just get this little thing darting around here. You can see this is how the Earth's eccentricity changes, and it goes through cycles, 100,000 year cycles, where it will go from almost being a circle to being slightly more elliptical. What causes it is the gravitational tugs from Jupiter and Saturn in the outer solar system. You know, the sun's pulling us this way in our orbit, and the outer solar system, you've got the big giants there, Jupiter and Saturn, are pulling us out, and it's the movement of them is what's giving us this 100,000 year cycle, regular cycle of changes. So Earth's current is 0.0167. That's what we are now. So we're not too far off a circle. It varies from almost a perfect circle through to being slightly elliptical over 100,000 years. We are now, this question someone asked me the other day, where are we? Are we moving more elliptical or more circular? We're moving slightly a lower eccentricity, so we're moving, part of the cycle moving slightly more circular. So isn't it credible this guy worked all this work, did it all out, and said, okay, every 100, he worked out where Saturn and Jupiter would be, the gravitational forces, he obviously knew their masses and how they moved and worked out, yeah, there's a 100,000 year cycle, guys. That's incredible, with no calculators or anything. But he worked all that out. So the effects of eccentricity, what does it do? Yeah, the more elliptical an orbit is, the bigger the difference between solar energy when it's at its perihelion versus aphelion. So it amplifies climatic conditions, essentially, what you're getting. And at the moment, once again, here's our little exaggerated diagram down here, where we are at the moment, the southern hemisphere, during our summertime, which we'll talk about shortly, we are closer, so we're getting warmer summers and cooler winters. The northern hemisphere, the effect is that moderates their seasons, so it gives a slightly cooler summer and a slightly warmer winter, so it gives a more moderate. But that all changes too, which we'll be talking about. But that's the effect of what eccentricity has. And it's a 100-year cycle, so it just amplifies the difference between seasons according to where you are in the orbit around the sun.
Why would it be 100,000 years? Because Jupiter and Saturn orbit much more frequently than that.
Yep. Sure, but they're all orbiting at different rates. He's worked it all out, yeah. I think, yeah, it's a miracle that he's worked it all out. But it's so, this is life, this is how it is, yeah. But yeah, it's 100,000 years.
And is it exactly 100,000 or is that?
Oh, you go and look at the end, it might be 99.8 or whatever, but it's roughly, to within a year, so roughly about 100,000 years. That's the figure that's quoted. Now, go and Google it and you might find, or it might be 100,001 or something like that, but it's roughly, it's just a nice figure to remember in your head, yeah. It's.
The other interesting thing, Chris, is that when the Earth is closer to the Sun, of course, it's moving faster.
Yes.
So it means that our summers are slightly shorter than the northern hemisphere summers, because they're at the aphelion phase, so the Earth is going slower. So the Earth
we get longer winters in the southern hemisphere and shorter summers. Yeah, we get cheated, but that will change in 13,000 years. That's going to change, guys. So it's okay. It's okay. And Winston Peters will still be in Parliament. Okay, so that's eccentricity. Axial tilt or obliquity, that's how tilted over the axis is of Earth, and that's it here. And it's, of course, that's what gives us our seasons. But we tilt, as you know, Earth is a 23.5 degree axial tilt. That's not set in concrete. That's at a 41,000 year cycle where it varies from a degree either side, from 22 and a half actually to about 24 and a half. Let's just push that up here. So it's the axial tilt that gives us our seasons. And this little diagram here, this shows in the middle of the year, you can see the northern hemisphere is tilted towards the sun, so they're getting more sun exposure, longer days, more intense sun. They're at summertime. We're tilted away, we get winter. And the same and the opposite, over the months of December, January, it's the southern hemisphere that is tilted towards the sun, so that's our summer, that's the northern hemisphere's winter. So it's that axial tilt that gives us seasons. And the current tilt, 23.5 degrees. It's a 41,000 year cycle between 22.5 and 24.5. We're halfway. Which way are we heading? We're heading to a less degree. So we're heading towards the 22.5. So our obliquity or axial tilt is actually diminishing. But once again, it takes time. It's a 41,000 year cycle. Why are we on an axial tilt? Probably caused by the early collision, which is the most favoured cause of how we got our moon is a giant impact, where Earth protoplanet, but when the solar system was about 500 million years old, it collided with another object and it set Earth on an axial tilt. And ironically, it's what makes our moon so special. Our moon is very large relative to the size of Earth, to its host planet, Earth, and it's our large moon that gives us our relative stability. And you might think, well, it's moving a degree or two. That's not too stable, is it? That's stable. Mars, which only has 2 potatoes for moons, probably captured asteroids, but no real moons, no serious moons. That varies anywhere between 0 degrees and 60 degrees. So it swings wildly. Historically, that's swung wildly. And we talked about how the moon formed and how the moon gives us more moderate climates and seasons, which is important for life. So, yeah, the axial tilt is decreasing. A lower obliquity, in other words, when it's more upright, tends to give you less extreme seasons. So you also starting to get build-up of ice at the poles, because a higher tilt, tilting overwards, exposes over that hemisphere summertime, exposes those poles to the sun, which starts to melt the glaciers, the polar glaciers. And it was all this whole concept that got Milinkovic starting to think about it all. He said, in particular, he was thinking of the northern hemisphere glaciers. His hypothesis was that the way the sun is and the earth is orientated and the way the earth orbits and stuff is all in cycles, and that would have an effect on glaciation. Whether if it's lower obliquity, you get glaciers, you're going to get more glaciation. A high obliquity, you're going to get a lot of melting going on. So with large obliquity, you get the extreme seasons and periods of deglaciation. So that's axial tilt. Precession. So precession is an interesting little concept here, and that's the bottom line, is the wobble. You know when you spin a top, it doesn't just spin like that, it spins like that, a bit of a wobble to it. In other words, it's the orientation of its axial rotational axis. And it's that wobble it's called precession. That's what a precession is. And that too has a cycle. It does a full cycle every 26,000 years. And that's why, and I said when Bill mentioned it, here it is here. That's just another little diagram of it here. Sort of shows it quite nicely how it maps out the rotational axis. Its orientation maps out a complete circle every 26,000 years. And what causes that? It's a tug, gravitational tug between the sun on one side and our moon on the otherwards. And once again, wasn't that brilliant? He worked that out. That between the two competing forces, that would alter the orientation of the rotational axis or the precession, and he worked it out. It was a 26,000 year cycle, and this guy worked it out in the 1920s. It would have been on paper, just incredible. And it affects the timing of the seasons relative to the Earth around the sun. And that's why he raised it when Bill raised that. Currently, when January, when we're a little bit closer, we experience our summer and the northern hemisphere is the winter. It's going to be the other way around. So our winter will be January, December, and middle of the year, it'll be our summer and the northern hemisphere's winter, because the axis, I might even have that in the diagram. Do I have that in the diagram? No, so I've just put here, so currently, that's where we are now. So axial precession, it makes it more extreme in one hemisphere and less extreme in the other. So in 13,000 years, it's going to be the other way around, where the northern hemisphere will get more extremes in solar radiation, and we'll get more moderate seasons in the southern hemisphere. So, but you've got to wait 13,000 years. So just bringing it all together, you've got these three cycles. You've got a 100,000 year cycle of eccentricity. You've got a 41,000 year cycle of the obliquity or the axial tilt. And then the orientation of the rotational axis, or known as the precession, that's in a 26,000 year cycle. So you've got these cycles going on. So then what he was able to do, not only that just is mind-blowing, any one of those three, but he did all those three, and then he brought them together. Worked it all out, just absolutely incredible to create this long-term pattern. And you can see here, this is sort of over many thousands of years in blue here. So here's the temperature of the Earth. Here's the years over many thousands of years. You can see in blue here the solar irradiance that you'd predicted by the Milinkovic cycles. And here is the temperature of the Earth as they usually find out through ice samples and so on. They can look back in history, the temperatures. And you'll see here the timing of the Milinkovic cycles is a fairly good agreement with the timing of the temperature changes. Not the absolute values, but the timing of the changes. It is matched over hundreds of thousands of years. He worked that out on pen and paper in the 1920s. Absolutely incredible. So I throw that to you. Now, over recent times, over the recent decades, it seems to have wandered off. Here we are here, talking the 1960, 1980 onwards. We should be now starting to head into in what we're calling a sort of like a mild ice age, where we should be cooling down. But over the last sort of 50, 60 years, the temperature of the Earth has been going up. That is the subject. I do not want to open that can of worms in this room, thank you very much. So I thought best I leave it there, and that's the subject of another talk. But you can see just of recent times, and that's what all this whole climate change debate now is all about, how it's been so good for, matched up so well for so long, and here we go in the last 40, 50 years, a lot of things have been happening, it's wandering off. So people will argue all sorts of things, but leave it there. So I just throw that in. I think it was worth talking about Milinkovic, because about a third of you put your hands up, you'd heard of it before, you're familiar with it, but 2/3 of you hadn't. You now know what Milinkovic cycles are. That's what they are.
But those cycles are the solar cycles. I mean,
There's the 11-year solar cycle you're referring to.
The trend down now might be part of the Milinkovic cycle, but the yellow up and down,
Yes.
the 11-year cycle,
Yes.
is just the solar.
Solar's correct. That's like almost like noise. Yeah, like nothing in biology. You're an engineer. You always have straight lines. Biology, you always, nature. You always have lines like that with trends. Yeah, but you're right. That's referring to the. But you can see the trend where it should be heading, but it's not.
But what you're saying there about the end trend of it trending down.
Yep.
Is more related to a Milinkovic cycle than the solar cycle.
Yeah, because these ones here look more like solar cycles.
The light yellow.
Yeah, the light yellow ones, but the dark one, this is where the Milinkovic cycles say we should be going. Yeah. You cut that out. So anyway, formation of the moon, which we've talked about. So the most widely accepted hypothesis, and there's a few out there, how we got the moon is either a circumplanetary disk formation, in other words, a disk formed around our planet as our planet was forming, whether we captured something, a large object that was going by, like an asteroid or a comet. Fission did a bit of our Earth as it was spinning around, just a blob just spin off, or the giant impact hypothesis, which we talked about. So who got D? Yeah, who thought D? Yeah, absolutely. That's the most widely accepted hypothesis. And it's when it's speculated that proto-Earth, when it was about 500 million years old, in orbit, and there was another protoplanetary object called, they've just called it Theia, about the size of Mars, about half the size of Earth, half the size, say roughly the size of Mars today. It hit the Earth at an oblique angle, gave us our axial tilt, and flung a lot of molten material into Earth orbit, and that coalesced to form our moon. And it's supported by the Apollo moon rocks that the astronauts brought back, and just analysis of the different isotopes. We went into length in talking about this, and they've had computer models how it would form, but there's always been some problems with it. But just a recent paper 2 years ago, they've run things through some supercomputer models, about 1,000 times higher resolution computer models with more particles and stuff, and they overcame all the obstacles, and it just seems to fit quite nicely. So that's the most favoured, or most commonly accepted by planetary scientists, how we got the moon. What is the name of NASA's project to return to the moon? Apollo 2.0, Starship, Artemis, or Blue Origin? Artemis, Artemis, absolutely. This is a nice little photograph here of Artemis 1, and that's NASA's SLS, Space Launch System there with its 2 solid rocket boosters, and there's your Orion capsule on top. So that's their launch vehicle to get the crew into space and get the crew sent to the moon. Apollo 2.0 was obviously a bit of humour. Starship is the SpaceX space system for getting the lunar lander up into space and then onto the moon, where the astronauts will then link in with it. They'll be in the Orion capsule, they'll rendezvous with it, and then take it down to the surface of the moon. And Blue Origin is the company that's developing also rockets in competition with SpaceX, and it's got a contract to build a lander in competition to Starship, one from SpaceX. And this is NASA's goal for a base camp, a very basic base camp by 2030. And the base camp will involve, it's got its lander over here, your Starship lander, and you've got a surface habitat here that should be able to house 4 astronauts for up to between 30 and 60 days. It involves also 2 lunar rovers. There's a 2-seater open plan one that's obviously just pretty much like the lunar rovers from the 70s, where 2 astronauts have to be in their spacesuits seated and on it. But there's also one by Toyota, have brought out the lunar cruiser, and that's fully pressurised, can house 4 astronauts. They don't have to be in their suits, and they can live in it for up to 45 days and go many kilometres away, and pretty much like a travelling station, if you will. So that's going to be a huge plus, and that's, these things are already well advanced and developed. the talk, we decided realistically they're looking at, with assuming there's no more delays or any catastrophes, you're looking at 2033 at the absolute earliest. You could argue that would be optimistic too. So where does NASA want to land and establish a moon base? Sea of Tranquility, the lunar South Pole, Taurus Littrow region, or near the lunar equator? I better think about that. And who thought B, the lunar South Pole? Absolutely. Sea of Tranquility, of course, was Apollo 11's landing site. Taurus Littrow was the region where Apollo 17 landed. And a lot of those early missions were near the equator because they're easy to land to. It's technically more harder to land at the poles. But what attracted them to go to the South Lunar Pole is that because the lunar axis doesn't have a big tilt, it's got about half a degree, if that's got no axial tilt to speak of. So it doesn't get extreme seasons, so you don't get the poles pointing towards the sun at any one time. They're always sort of relatively upright, so those big deep craters at the poles, they're permanently in the shade, and they call them PSRs, permanently shaded regions. They have never, ever, ever in their history since the moon existed seen the light of day. So you've got frozen ice there, which is important for numerous reasons. One is, of course, it's water, and water is one of the important resources to drink, to cook your food with, to water your crops with, split it with electrolysis to hydrogen, oxygen to breathe, hydrogen, oxygen for your fuel, for your rockets, and so on. So it's invaluable, but it's really, really heavy. 1 litre is 1 kilogram, and weight means expense for getting it up there, so you've got it waiting there for you, your most valuable resource. But also, this is pristine ice from the very beginning of the solar system. It's great geology to study it as well. So that's why they want to go back to the lunar South Pole. North Pole's very similar conditions. It's just as rugged territory as the South Lunar Pole. I think they just cottoned onto the South Lunar Pole first. Sorry. So that's where they want to set up their base. So Earth's water gave a talk, and someone bailed me up after a talk. They said, look, nothing related to this topic, but where did Earth's water come from? And so where did Earth's water likely come from? A, comets and asteroids bombarding Earth. The solar nebula, that's the big cloud of gas and dust that shrunk down to form the sun and the planetary disk. Hydrated minerals and a volcanic outgassing, or all of these. Who got all of these? Yeah, a lot of the popular one, I remember I was talking to this guy, this was quite a few months ago, and I said, look, I believe that most of it's come from comets and asteroids, and it's thought to be mainly asteroids. And his reply was, jeepers, but there's an awful lot of water on Earth. And I said, well, there's an awful lot of comets and asteroids as well. And I'm just going to jump ahead, I'm going to come back to the slide, because here's a little fun fact for you. Water covers 70% of the Earth's oceans. We think it's pretty deep and it all looks big, and you look at the ocean, but all the ocean's water by mass is 0.023% of Earth's total mass. The Europa, I did a talk at Hibiscus Coast, and I'll do it next year, on the Europa Clipper mission to Jupiter's moon Europa. That's the evidence, strong evidence suggests it's got a subsurface, got an icy surface, a subsurface global ocean. That moon is just, Europa is just a little bit smaller than our moon. So roughly comparable, just a tad smaller. But that global ocean has got at least twice the amount of water of all the Earth's oceans, water's total. So, our oceans in the big picture aren't that deep. We think they're deep and stuff like that. It just puts it in perspective. Titan, the moon, Saturn's largest moon, they estimate there's somewhere between 10 and 12 times amount of water on Titan than there is on Earth, all Earth's oceans. So it just puts it in perspective. We think, we're the water planet, we've got so much water. Yeah, we've got a lot of water, but put it in perspective, guys. So, anyway, so they think most like comets and asteroids, that's called extrinsic, then there's intrinsic. Out of that extrinsic, historically they've thought probably from comets, because they're the big icy objects from the outer parts of the solar system. But looking at isotopic ratios of hydrogen and water, its best match is not with comets, but with asteroids from the outer part of the asteroid belt, carbonaceous asteroids is the best match. So they think most likely primarily the water's from all of these sources, but primarily from the water-rich asteroids in the outer regions of the asteroid belt, where most of it's come from. Yes, there's a lot of evidence suggesting in that solar nebula, the big cloud of gas and dust, that there was a lot of water vapor in there as well, and a lot of that just condensed into water, it became incorporated into Earth. And there's a lot of hydrated minerals. There's a lot of water locked up inside Earth, just with hydrated minerals and minerals and volcanic outgassing. All this water vapor is coming out. So it's from all of those sources, but primarily it's thought of these water-rich asteroids. Okay, and then I did a talk on the Milky Way at the beginning of the year. I thought I'd done a pretty good job, a comprehensive thing. Someone says, put their hand up, but you didn't mention anything about Fermi bubbles. So here's your Fermi bubbles, all right? So what are Fermi bubbles? So Fermi bubbles here are these big bipolar sort of lobes, if you will, of high energy gamma ray emission. So here's our Milky Way galaxy, and that's 100,000 light years across. But extending out the Fermi telescope that detects gamma rays, that's what's been named after, picked up these huge big lobes of high energy, of tenuous gas, high energy emitting gas here, emitting these gamma emissions. So the question is here, what are they most likely caused by? And they don't know for sure, but it's, once again, an educated guess, a good educated speculation, either A, multiple supernova, B, black hole mergers, the Milky Way's central supermassive black hole, Sagittarius A star, or white dwarf and red giant binary systems. So have a think about that. Who got C? Yeah. So once again, it's not known, but it's speculated that, let's just bring this picture back again. It's speculated that you've got this supermassive black hole in the middle. Early days of the galaxy, there would have been a lot more material. It would have been active and spewing out jets of material at high velocities and just emanating these high energy gamma rays. So yeah, that's the thought there. So whoever that was, in fact I know it was, they're not here today, I know who it was. And there you go, there's your Fermi bodies. So that's it. I hope you've enjoyed the annual fun quiz and revision. It's a new topic. Thank you. Good. Thank you. So hope you all have a very Merry Christmas and Happy New Year. Drive safely home. And the next we resume the Introduction to Astronomy talks is February. And Jonathan Park's going to be doing a talk on the moons of Jupiter then. So that'll be fun. So did everyone get a handout? Yeah, so I put the Milankovitch cycles and brown dwarfs on there because they were the two new subjects for tonight. So all good. Right, we're all done. Does anyone want any more chocolate?